How does a service like Netflix just know what movie you're going to click next? Or how does your bank decide, in literally a split second, if a transaction is fraud? Well, it's not magic. It's actually one of the most fundamental and powerful algorithms in machine learning. And it's all designed to answer a really simple but critical question: yes or no. And today, we are going to break down exactly how it works, from the ground up.
So this is really the core question we're tackling. You know, whether it's a medical system that's trying to flag a tumor as malignant or benign, or just a simple spam filter deciding if an email is junk, machines are constantly making these binary choices. The real question is, how do they get so good at it?
All right, first things first, we have to understand the type of problem we're solving here. It is fundamentally different from trying to predict a number, like, say, the price of a house. We're not asking how much. Instead, we're asking which one. Okay, check this out. On the left, you've got regression. That's for predicting a continuous value. Think stock prices, temperature, stuff like that. On the right, you have classification, which is our focus today. That's all about predicting a category. Is it spam or not spam? A cat or a dog? Now here's the funny part. Despite having regression in its name, logistic regression is the absolute king of binary classification. So you might be thinking, why can't we just use a simple straight line, like we do in linear regression? Well, think about it. If we say yes is 1 and no is 0, a straight line can easily shoot way past those numbers. It could predict a 1.5 or a negative 0.5, and what does a negative half tumor even mean, right? It just doesn't make any sense. We need a much smarter approach. So that straight line approach is out. We need something better. To get there, let's build some intuition. Forget about all the math for just a second, and I want you to imagine we're training a very, very smart bouncer for an exclusive club.
Now, this bouncer's job isn't to guess how old someone is or how tall they are. No, his only job is to make one critical decision. Should this person get in, yes or no? He learns by watching, looking at past guests, and remembering who caused trouble and who didn't, based on things like what time they showed up or if they were on the VIP list.
And here is the absolute key to the whole thing. Our bouncer doesn't just think in yes or no. He thinks in probabilities. He calculates a confidence score. This percentage is what makes the model so incredibly powerful. It's not just making a blind decision, it's telling us exactly how sure it is about that decision. And believe it or not, there's a beautiful piece of math that acts just like our bouncer's brain. It's called the sigmoid function. This is the secret weapon. It's this elegant S-shaped curve that takes any number, I don't care how high or how low, and it squashes it perfectly onto a scale between 0 and 1. A big positive score, it gets really close to 1. A big negative score, it gets really close to 0. It's the perfect translator for our yes-no problem. Okay, enough theory. Let's get our hands dirty and see how we can actually build this bouncer using Python. We're going to tackle a really important problem, diagnosing breast cancer, and we'll do it all with scikit-learn. So here's our mission. We're going to classify a tumor as either malignant, which we'll label as a 1, or benign, which we'll label as a 0. Our input features, what we call X, will be 30 different measurements of cell nuclei, things like their radius and texture. And our target, Y, is that final diagnosis we want to predict. We're going to follow a simple 4-step workflow here. And honestly, you'll use this for just about every machine learning project. First, we'll load and explore the data. Second, we'll pre-process it to get it ready for the model. Third, we train the model so we can find the patterns. And finally, we'll see how well it actually did on new, unseen data. Okay, so we've loaded the data, and the first impression is that it's super clean. No missing values, which is great. But, and this is a big but, look at the scales. The mean radius is a number around 14, while the mean area is way up over 650. This huge difference in scale can really throw a model off.
And that is why this step is so critical. We use something called a standard scaler to put all of our features on the same level playing field. This just makes sure the model doesn't give more weight to a feature just because its numbers are bigger. Think of it like converting feet and meters into the same unit before you compare them. We also split our data. We'll use 80% to train the model, and we'll keep the other 20% aside to test it later.
And you won't believe how simple the actual training is. It's just one line of code. Model.fit. That's it. In this one step, the model looks at all that training data, and it learns the perfect importance or weight for each of those 30 features to best predict the final diagnosis.
So our bouncer is trained. Now for the moment of truth. It's time to see how well it actually performs on that 20% of the data that it has never ever seen before. Did it truly learn the patterns,
Or didn't it just memorize the answers from the training set? Let's find out.
And our number one tool for judging our model is something called the confusion matrix. It might sound complicated, but it's just a simple table that gives us an amazing breakdown of our model's performance. It shows us not just what it got right, but exactly how it got things wrong.
Let's break this down real quick. The top left and bottom right boxes, those are our wins, true negatives and true positives. The model nailed these. The other two boxes are where the errors happen. A false positive is a false alarm. Not great, but manageable. But the most dangerous error, especially in medicine, is the one on the bottom left, a false negative. That means our model said a tumor was benign when it was actually malignant. This is the one we absolutely have to minimize.
So our model clocks in with an accuracy of about 97%. And that sounds fantastic, right? But hold on. Accuracy by itself can actually be a trap, especially when the cost of one type of error is way, way higher than another.
And this is where two other metrics, precision and recall, become super important. Precision asks, of all the times we cried wolf and predicted malignant, how often were we actually right? But recall asks a much more critical question. Of all the tumors that were actually malignant, how many did our model successfully catch? And this is where that probability score we talked about earlier becomes so useful. We can actually tune our decision threshold. To get a higher recall, we could tell our model to flag anything with over, say, a 30% chance as malignant. We'd get more false alarms for sure, but we'd also be much less likely to miss a real case.
All right, let's bring it all home. What have we learned? Let's quickly summarize where a logistic regression really shines, and also where it has its limits.
So here's the deal. You want to reach for logistic regression anytime you have a binary, yes or no classification problem, especially when knowing the probability of an outcome is important. Its biggest strengths are its speed and the fact that it's super easy to interpret. Its main limitation? It works best when your two groups can be separated by a pretty simple line or curve. If you've got really complex, tangled-up patterns, you might need a more advanced model.
But what's the real takeaway here? It's that you don't always need the biggest, most complicated tool in the toolbox. Logistic regression is really a testament to the power and the elegance of simplicity. For a huge number of real-world problems, it's not just a good place to start, it's often the perfect solution.
Like and subscribe for Simplify Tech, explaining one concept at a time, simplifying the technology and AI.